How are you, everybody who is watching this video? I would like to take this opportunity to welcome you into our workshop 4, where that we are going to learn how we can solve a real-life engineering problem. So my name is Olenjolai, and I would like to invite you into this workshop, which are actually it's a link of the workshop. We had workshop 1, workshop 2, workshop 3, and this is workshop 4. Our theme or the themes of these workshops is actually to build the concepts on top of it. Because whenever you want to solve a problem, you have to follow a particular algorithms or a particular arrangement. But one thing which I want to ask you, firstly, in order for you to master this stuff, you should love them. But these contents can help any beginner students, whether in ordinary diploma or whether in undergraduate level, even for advanced secondary schools who wish to study a degree in electronics engineering, or degree in telecommunication engineering, or degree in electrical engineering, or degree in computer engineering, or degree in biomedical engineering, or degree in computer science. Sometimes these informations are a little bit important because you are going to deal with computers or just smart devices. So, I would like to ask you that, have a fresh mindset, because the theme of this actual that we are trying to build the mindset in you, but later on we'll put our hands into work. So simply, the slogans or the policies that we have, it's mind and the hand. That's the slogans of any effective engineer. Mind used to think, and your hands used to do the practicals that we are thinking to do in order to solve that particular problem. So I have some local students who have joined me in this class, and let me just acknowledge them. Good morning, class. Good morning, sir. Good morning, class. Good morning, sir. How are you? Why are you here? Why are you in this class? Okay, others they are saying for studying electronics, for learning electronics. Others they say that just to see what is going on in this world. So if that's the case, good morning also for the online community. So let us start our class. So let us do the quick review of the previous workshop. Quick review of workshop 3. So I will use my local students who are in this class to remind us what we have learned in previous class. Hey! Hello! So we learned first of all the detailed block diagram of linear power supply unit. How many blocks does it have? 4 blocks. So let me just redraw them, because this one you have to draw in your mind. The first block is called what? Speak loudly, students. Step down transformer. Is it a unit or not a unit? Why it's not a unit? It consists of what? One component. One electrical or electronics component. But this one is electrical component. And then you have what? Rectifier. Get in. Rectifier what? Unit, because you have more than one electronics or electrical component. Then, the next block is what? Filter unit. Filter unit. The next block is what? Voltage regulator. So voltage regulator unit. And then the next block is what? Load. Are you a load or what are you? Who are you in this block? You're a load. You can consume this power that's given by the linear power supply. So in workshop 3, we've opened this block and they've learned a lot of information. Right? But I told you that engineering is all about numbers. It's all about tables. It's all about graphs. It's all about diagrams. It's all about formulas. Right? Just to remind you some few keys, we'll be talking about the numbers that we've been discussing. But just to remind you, one of the formula or some formulas that we've discussed is the relationship between maximum voltage and root mean square voltage, which is under root of 2 times root mean square voltage. But another formula we've discussed about voltage from peak to peak, which is 2 times what? Maximum voltage or peak voltage. So those are some few formulas that we've recalled. Actually, we've just applied the concepts of root or square root, multiplication. Square root and what? Multiplication. But again, in case of the diagrams, okay, we draw just the schematic diagrams of the center tape transformer and non-center tape transformer. So just to remind you, this is the one of the diagrams that we drew in previous workshop. And these are just, this represents the primary coil, and this represents the secondary coil. Secondary what? Secondary coil. So this one, this is primary coil, and this is secondary coil. So this is non-centered. So if you wanted to draw the schematic circuit diagrams of the centered step-down transformer, this is the symbol, right? And then we spoke something that if here we have 9 volt, here we have 0 volt, here we have 9 volt. But if you measure the potential difference between terminal 1 and terminal 3, or terminal 1 and 2, then we get 9. Or terminal 3 and 2, we get 9. But if you measure between terminal 1 and terminal 3, we get 18 volt. So we say that the step-down transformer actually that has more advantages more than non-center tape step-down transformer. So the center tape step-down transformer has more advantage compared to what non-center step-down, non-center tape step-down transformer. Why? Because you might get two different values of voltage at the output. Okay? And then it's another thing that we discussed about the table. So we had our table, which we call the table 1. So we have drawn about table 1. In this table 1, actually that we had how many columns? Students, how many columns? How many columns? 4 columns. So the first column actually represents electrical parameter, right? Then here we have what calculated value, the one that we've been calculating, right? And then another column is labeled as what? Simulated value. Jacqueline is not speaking. Then the other one is what? Measured values. So we managed to fill this column, the first column and second column. Then we say that if you are going to use either online or offline electronic simulation tools, we are going to fill the other column. If you go for the hardware, for the testing or building this circuit on the breadboards, we'll fill this part. Or whether that we build on the variables or the PCB board, we fill this part. Right? Right? So we still have 2 empty columns. But another thing that, which we have discussed, is about the graph. So from there, I began to build the concepts of the graph in engineering. So this is the voltage, y-axis represents voltage, and the x-axis represents time. So then the graph actually that we say that this is the input voltage, which is 220 voltage or 240 voltage, right? And then we say that this will be our output voltage. Our output voltage. Okay? So if that's the case, so this is V in, and this is V out. Okay? So these are the graph, which are sinusoidal graphs. So if you have a oscilloscope which can sustain this amount of power, you can do this measurement. But you cannot do the measurements for the input voltage according to the by using the normal electronic oscilloscopes, because 240 volts is higher voltage rather than the maximum amounts of the voltage which the oscilloscope can sustain. Ever come? So today we are going to open the second block. So we opened about this one. We're going to open the second block. Rectifier unit. I try my level best. I assume that you have theoretical concepts of rectifier. Right? That's the assumption I have to make. So my intentions is actually to teach you how you can design. How you can design. Or how can you build up the rectifier unit. Or how can you make a good choice of the components that you are going to use in rectifier unit. So my responsibility is just to open the block. So that's the assumption that I have to make. Otherwise, we need more workshops to go through. Are we together? But remember that I told you that linear power supply is a fundamental power supply that we are using in electronics, especially whenever that you want to build a prototype. Okay? So you have to make sure that you concentrate, you learn. And the challenge that I used to face whenever I teach students this concept, many students, they assume that they know. They have enough knowledge about linear power supply. But the fact is, there's no limitations of the knowledge about the power supply. Even if you want to go into the depths, more than what I'm going to teach. Mvunye Suleiman. So rectifier unity, actual, what the main function of this unit? So rectifier, let us just mention that once. Rectifier, just to remind you. Rectifier unit is the unit, that what? Convert. Convert or convey? Convey to what? AC voltage. Or AC signal. Or AC signal into what? Usually, theoretically, when we have been introducing the concepts of rectifier, we used to tell you that into DC, right? But when we have been learning the DC or the outputs of the rectifier unit, it's not pure DC, right? So what is the technical name? Pulsating. So pulsating. DC what is signal. So some of the students, I taught this concept before this class, and you might say that it's enough. I asked you to write because I'm going to add some key points. I'm going to write some key points which can help you. I'm going to add some key points which I did not teach you in previous class. So pay attention, write, take a note, ask questions. Then we said that in electronics engineering, there are how many types of rectifier? Limi. How many types of rectifier? There are 3 types of 40. Of rectifier. Of rectifiers. The first one is what? Half wave rectifier. The second one is what? This one uses what? 1 diode. Right? The second one is what? Full wave rectifier. This one uses what? Kevin is at the interest door. 2 diodes. Get in. Then the third one is what? Clap your hand for coming of Dixon. Clap your hand, please. Stop writing, clap your hand. Congratulate your class representative. Come. You could not sit there. So sit with Mexina today. Matatu. Take out that bag. The third one, we call it what? Bridge rectifier. Bridge rectifier. So here we are using 4 diodes. I remember that when I taught this concept last time, some of the students did not understand it clearly. So take this advantage to learn it. So bridge rectifier unit. Bridge rectifier, full wave, bridge rectifier. So bridge rectifier. Class A, half wave rectifier. Full wave rectifier. Bridge rectifier. So when we've been introducing you this concept, we taught you about the advantage and disadvantage of each type of the rectifier. So whenever you want to make a choice, you might be asked your questions, why did you prefer to choose a full wave rectifier and not a half wave rectifier? Or why did you prefer to choose a full wave rectifier and not a bridge rectifier? So you should have technical reasons. Or you have to state advantages of your choice of the rectifier that you have chosen over what disadvantage of the other ones that which you have been asked that why didn't you choose them? Okay? Yeah, because we used to make choices in engineering or in electronics engineering with reason. So you have to learn how to reason. Not just that I took the bridge rectifier because there's 4 diodes. But somebody can come and challenge you. Buying 1 diode and buying 4 diode, which is economical. For instance, a diode is 1,000, right? You're spending for 4,000 and spending 1,000, which is more economical? 1,000, eh? So why didn't you check the economical factor rather than the performance factor? So from there, because you've been claiming, you say, sir, you know, the half-wave, whatever. No, just give the evidence that make you to choose the more expensive alternative rather than the cheap alternative. Right? So ask your neighbor, why are we going to choose the bridge rectifier and not the full wave rectifier? Ask your neighbor. In most, keep asking and listen. In most of electronics design, we choose the bridge rectifier. The bridge rectifier due to bridge rectifier. So the question now, why? So we choose the bridge rectifier. So the question now, which I ask your neighbor, why? So keep asking your neighbor and try to challenge him or her. Why it's not a full wave rectifier? Why do you want to? Because actually here you have seen the challenge. This maybe might have some advantage over this one. Maybe it's economical, right? But this one is expensive. Why do we buy 4 diodes rather than 2 diodes or rather than 1 diode? So ask your neighbor and challenge him or her. Give me the technical reason. Because in engineering, we have to try our level best to build this system which are economical. For instance, the mobile phone that you have, if it could be sold 1 million, I believe that you could not own it or you couldn't even buy it. Can you take your boom 1 and boom 2 and buy a mobile phone? Boom 1 plus boom 2, because I think that is 1 million. Right? Can you take it to the shop and buy a phone just for calling and WhatsApp? Why there is a features mobile phone which in Tanzania we call Tiki Swaswado, which costs 50,000. Can you buy a phone, take it 2 booms and buy a mobile phone, then you are bankrupt for the entire semester. We'll have a binary number. And then just for the matter of for the theme of 40, calling, texting, and WhatsApp, because that's the main function that you are using every day in a mobile phone. So is it logical? Then you call your father. Father, I've received the boom and I bought the phone. So I'm bankrupt. Is it possible? So if it's not possible, why are we going to buy 4 diodes rather than the 2 diodes or 1 diode? So ask your neighbor. I don't need to hear what you are discussing. Okay, so in most of electronics design, we choose the bridge rectifier. Now I'm building after a daily. Maandika uongo na ukweli. Okay, so because we know that, so let us go into the next important part. The schematic, the common schematic circuit diagram. The common schematic circuit diagram of the bridge rectifier, because I say that our focus is just design. Bridge rectifier is the common schematic circuit diagram of the bridge rectifier is this one. So even online students, so you can ask some other students, why do you choose bridge rectifier and not, which is expensive, and not the half wave rectifier, which is the cheapest, or the full wave rectifier, which is moderate, price is moderate. So why? Urasa? So this is the schematic circuit diagrams that we use to draw without taking care about its output and its input. So this is the common schematic circuit diagram that we've been taught when we've been introduced about the concepts of 40 of diodes. So you just draw like this, and then see we have a diode like this. Then here it is. So we might call maybe this diode 1, this diode 2, this diode 3, this diode 4. So this is the common schematic circuit diagram. But with that common schematic circuit diagrams, we didn't bother about the input of the rectifier unit, and we didn't bother about the output of the rectifier unit. What we just wanted to present 4 diodes in a particular configuration to establish a bridge. Another question, why is it called the bridge and not mangoes? Why is it called a bridge and not a road? Because bridge, we have bridge on the roads, right? Why is it called a bridge and not a road? Or not a tower? Why didn't we call it a tower rectifier? Think. Okay. So this is the schematic. So this is, for this workshop, you can say that figure 1, the common schematic circuit symbol. The bridge rectifier, the common circuit, no, so circuit, not circuit diagram, excuse me. The common schematic symbol. So no correction. The common schematic symbol of the bridge rectifier is this one. The common schematic symbol of bridge rectifier. So when we have taught, we have introduced the concepts of the bridge, we did not teach you about the input and the outputs of the bridge. Right? We just drew the 4 diodes in that configuration. That's all. Right? Right? And actually, this concept is it has a close relationship with what? Galvanometer. If you do remember about electrical devices, because we used to put a galvanometer here. Right? Do you remember? Okay, fine. So, and then, so we said that, so figure 1 can be represented in the schematic circuit diagram, or in the schematic circuit diagram, with regard to 40 of input and the output. Regard of input and the output. Because I remember how the atmosphere was when I taught this concept a week ago. In the special, to transform Johanna from this schematic circuit diagram into series configuration. So Johanna, you have to listen double here. Right? So then now we want to redraw this schematic circuit diagram in this way. Examine, check your neighbor. Is he or she drawing? And drawing by using a pencil, not a pen. Examine your neighbor. If he or she is drawing by using a pen, ask him, are you okay? Ask him or her, are you okay? Just ask a simple question like that. Are you okay? Just ask a simple question like that on my behalf. If you see your neighbor on left hand side, right hand side, drawing the figures by using a pen. Ask him or her, are you okay? Just ask that question, are you okay? I believe that you'll find or you'll meet his or her smile, because he or she knows his situation or her situation. So do you see? So stop drawing. So in most cases, for the linear power supply, the input, get in. The input we use to supply the input of rectifier unit from the low step-down transformer, right? Right? So you may just name them. That was the 1, that was the 2, that was the 3, that was the 4. Okay? Eh? Okay. Then, so this one will be input 1. And this one will be input 2. Okay? Eh? Johanna, that's what we drew last time? Johanna is still listening double. Yes. So it means that this is one terminal from there, one terminal of step-down transformer, and this one is another part from a secondary terminal of step-down transformer. Are we together? Are we together? So input 1, input 2. So these are the terminals where we connect the step-down transformer. Okay? So we call it input 1 or input 2. But actual, we might use the symbol of sinusoidal. So this is the symbol of sinusoidal. I say this, stop drawing. Stop writing, stop drawing. Again, we say that we still have other 2 terminals. So with this terminal, we say that this one will be connecting with ground. And this one is where we are going to draw our pulsating signal. So by that time, I just say that this is output, let's say output 1, and this one, so I just call the output 1, and this one is output 2. So for this output and for this configuration, this one is used to be negative, and this one we might present by using the positive. In other words, Shukuru. In other words, this one we can call it ground. So this we have to connect it to the common ground. And engineering students, I want to tell you that one of the sensitive and important part in any designs of electronic system is common ground. If you have a component which should be connected to the common ground and it's being disconnected, it won't function. So when you talk about common grounds, we don't mean about the soil or the land. We mean about the negative. Okay? Okay? Are we together, class? Are we together? To represent the input and output on this configuration is simple. But now to present in another configuration is the challenge. So with this case, or this configuration that you are familiar with, let us explain a little bit about how this bridge rectifier will rectify the AC voltage or the alternating voltage. Simple. We say that you find that here we have a positive half cycle and here we have a negative half cycle, because these are the 2 terminals where we connect UCOT with the secondary coil of the transformer. Okay? Okay? So if the secondary coils of the transformer, the alternating voltage is actually fluctuating. There's a positive half cycle and negative half cycle. Right? Then within a fractions of second, positive half cycle, negative half cycle. Positive half cycle, negative half cycle. For instance, for the alternating voltage, it completed 50 cycles in 1 second. So what the time to complete 1 cycle? 50 seconds. 0.005 second. It completed 50 cycles. the AC, the domestic pattern you have, in 1 second. Then, what the time for the OT? For the 50, for the 1 cycle. You cross multiplication, right? Then X is equal to what? 1 over OT, 50. So it means the time is what? 0.2. So it means that the alternating voltage complete 1 cycle in what? In 0.02 second. So this 1 cycle has a positive half cycle and negative half cycle. So that positive half cycle that will be fade at this point will be defined as the positive terminal. Because we have a cathode and anode. Remember that this is the anode of this diode 2, this is the cathode. Pascal, Joseph, this is the anode, this is cathode. This is anode, this is cathode. This is anode, this is cathode. So you know that from this fundamental principle working of a diode can be either forward biased or reverse biased. So when the positive terminal of the battery is connected to the anode and negative terminal of the battery is connected to the cathode, the diode will work in forward mode and will be allowing the conduction of 40 electricity, right? When you connect the positive terminal of the battery to the cathode of the diode and negative terminal to the anode of the diode will work in reverse, and it will provide a very high resistance to the flow of current in such a way that it will not conduct electricity. That's the fundamental principle of the single diode. So whether they are 20, the principle is still the same. Are we together? So for the alternating voltage, we say that if it completes 1 cycle, it means that 1 cycle, when I say cycle, I mean about this one, not this one. This should have a constant, what? Constant radius. But this one is not necessary to have a constant radius. Right? Right? So this is 1 complete cycle. So this is positive because it is in positive side. This is positive half cycle and this is negative half cycle. So when a positive half cycle of the alternating voltage fade to the anode of the diode and the negative half cycle is fade to the cathode of the diode, that diode will be in forward mode. Right? When a positive half cycle of the AC is fed to the cathode of the diode and negative half cycle is fed to the anode of the diode, then the diode will be working what? Will be working what? Ask your neighbor, did you understand? Ask your neighbor again, did you understand? So here we have a positive half cycle. Hey, let us. Positive half cycle. After what is 0.01 second. Because 1 cycle is complete after 0.02 second. So it means that the positive half cycle is being made within 0.01 second. And another negative half cycle will be taking a time of 0.01 second. That's how you have to learn the stuff. Stop claiming. So this is positive. So when this positive, this is cathode and this is anode. Which one will you conduct? Diode 2 or diode 1? Diode 2 will conduct up this point. Then at the same time we have what? We have what? Negative. We have negative. Right? Negative is connected to what? To anode for diode 3 and to cathode of diode 4. Which one will you conduct? Diode 4. Why? Because the negative is connected to what? Right? To the cathode. And the positive cycle is connected to the anode of this one. Okay? So for that case, diode 2 and diode what? 4 conducts. Then within 0.01 second, the process reverse. Right? The negative half cycle. Then here we have what? We are going to have a negative half cycle. And here we are going to have a positive what? Half cycle. Right? So the positive half cycle connected to what? Anode and cathode, right? Which one will be in the forward bias? Diode 3. Okay? Because the positive is connected with the anode. Okay? And then here we have negative. We have cathode and anode. Which one will conduct? Diode? Simple like that. So for that case, diode 1 and diode 3 conducts. And when they conduct, they are in series. Are we together? So we can represent the concept I have taught you in this diagram. So you say that, so now we are going to have two operations. The first one, we are going to have diode 1, or diode 1. And then so you are going to have diode 2. And then this one. So here we have, this is what? So diode 2, no, diode 3. Or let us start with this one, diode 2, because you understood diode 2 and diode 4 before diode 1. Or, within a fraction of a second, we are going to have what? Diode 4, conducts. With diode or diode 2. Let us start diode 2, because for you always count a number in ascending order. So if you say that diode 4 and diode 2 for you, you reject that I do not understand. How comes that diode 4 start with? Diode 1. You cannot say diode 3 and diode 1. Why? You need a simplicity in your thinking. Right? So this is in forward bias, while this one in reverse bias. When this is in forward bias, this is in reverse. Are we together? Are we together? So the diodes which are conducted, they are in series. And the diodes which are not conducting, they are what? In series also. But in reverse bias. So just to present the concept, listen, stop writing. When here we have a positive half cycle, and here we have negative half cycle. Stop writing, look. So this, diode 2 and diode 4 conduct. At the same time, here we have what? Negative half cycle. And here we have what? Positive half cycle. Right? Right? After 0.01 second, the process reverses. Here you are going to have what? Negative half cycle. And here we are going to have what? Positive half cycle. So is this in reverse? Right? Here, in reverse bias. And here we are going to have what? Negative. And here we are going to have what? Positive. This is in forward bias. So the process repeats over and over and over until you die. Once you die, the process still continues until the rectifier stops working. That's the end. Or one of the diodes get damaged. Are we together? Okay. So it is clear. It's not like last time. Johanna, is it clear? Now you understood it? Yes, because previously you used to cram. And you used to cram because we used... You do know that why this is a little bit challenging? When we taught you the concepts of the diode, especially for the forward and reverse bias, we just taught you when we have a DC source. We have a positive and negative. Right? So in terms of alternating voltage, it's a little bit challenging. But you claim that when diode 1 conduct, diode 3 conduct. When diode 4 conduct, diode 2 conduct. So you have to memorize when diode 1 conduct. Then what? Diode 3, odd number, and even. For instance, if I change the numbering, you say, I didn't understand. Because here we have what? Even number, right? And that's the simple way to keep the information sometimes. It's not bad. But be flexible. When the process reverses, don't say that it doesn't work. It's just a matter of, for instance, I can call it diode 1, diode 2, diode 3. I can call this one diode 1, diode 2, diode 3, diode 4. Don't claim that this always should be diode 1. The one on the top, on the left, is always diode. Okay, so listen. The sensitive we discussed in previous workshop 3, we say the transformer will have 4 important parameters. The first one, root mean square output voltage, right? The second one, maximum voltage, right? The third one, frequency of alternating signal. The third one, you who were not present last Saturday, these are the materials that we have covered, but I'm adding the value, right? And the fourth one is what? Output current, right? So for the rectifier, the 2 sensitive parameters are output current and maximum voltage. Why? Because, stop writing. This is the reason. Here, we say that, listen, stop writing. This is alternating voltage that we are feeding to the rectifier. And this one has a maximum voltage, or peak voltage. It also has a root mean square voltage, which is output, right? And this is 0. So and also you have another signal. You might find that we have a root mean square for it, and and maximum voltage. So then, this signal, we fed it into rectifier unit, right? So our expectation, we expect to get a DC. This is time, this is volt. Okay? So for this case, we say that we expect the DC to be a constant signal. If you wanted to build it or to design a power supply of 12 volt, we expect it to have a constant 12 volt voltage. So for the DC, we have only 2 parameters for this case. If you are building the positive or the linear power supply which is providing the positive voltage. So it is positive 12 volt and 0 volt. So the only parameter which can, which actually the AC to DC converters use is maximum voltage and maximum current. Why? Because the DC voltage or the DC signal should be constant. Okay? Remember the root mean square voltage contains actual, or it contains all the points of this curve. But the maximum point is only 1 point. I have told you last time. Only one point. So the rectifier will be sensitive with the maximum voltage and maximum current. Okay? Okay? Maximum voltage, maximum voltage. Rectifier will not be responsible with root mean square voltage or root mean square current. So if that's the case now, listen. So this is just to give you this is rectifier unit, to give you just the overview. So listen. So if that's the case, you say that we can have these kinds of 40 of another schematic circuit diagram. So you say the schematic circuit diagram of what? The schematic circuit diagrams of a rectifier. Of what? Schematic circuit diagrams of the bridge rectifier. It is one. So you're going to have actual 2 diodes conducts alternative. So this is diode. So listen. This is diode 1 or diode 3. No, diode 1 or diode 2. This is might be diode 3 or diode what? Diode 4. This is anode. This is cathode. Then we have a voltage source here. And this voltage source, we say that positive and negative. Then we connect it in this configuration. So this voltage source, we say that it's a maximum value of output of the transformer. Wait. So this is maximum voltage. This is supply, maximum what? Maximum according to the type of the transformer or according to the specifications of the transformer that you chose. So don't limit. It depends. You have chosen a step-down transformer or a or you have chosen a step-down transformer of which specification? Eliakim, of which specification? So if you have chosen the ones which give the output voltage of 12 volts, so here we are going to have it, see, maximum voltage. Stop writing. Stop writing. The diode itself, it's used to consume power. It's used to draw power for the particular purpose. So here we are going to have voltage drop through the diode. So diode 1 or diode 2. And here we are going to have a voltage drop of diode 3 or diode 4. Here also you are going to have of diode 3 and diode 1. So, because I know that you might forget this information, and I know this information are important throughout your life of engineering. So let me just write diode 1 and the diode 3. So these are the voltage drop. If you remember the fundamental concept we taught you about the diode, when introduced for the first time, we told that the diode, the architecture of the diode, or the diode, actually is a combination of N-type semiconductor and P-type semiconductor. So when you combine the N-type semiconductor, which is rich with electrons more than holes, and P-type semiconductor, which is rich with more holes more than electrons, then there's the kinds of the repulsions, right? The kinds of what? Because there is a flow of holes and electrons within it. So actual, what you will come up. So any diode should have a potential barrier, right? Should have a potential? So if the supply voltage fails to overcome the potential barrier, that diode will never conduct electricity even if it's connected in forward bias. So the first responsibility of the supply voltage is actually to overcome what? The potential barrier of any diode conducted in that network. Are we together? So actual, we have three materials that we use to make semiconductor device. We have silicon, and also we have germanium, and also we have we call it gallium arsenide. Yes, gallium arsenide. So which is actually a compound. But we taught you fundamentally, if it is what? Theoretically. If it is silicon diodes, the potential barrier is what? 0.7 volt. That is theoretical. But when you measure, you'll never find 0.7 volt. Okay? Okay, that's why that we say we have a range. 0.6 up to 0.8. Those are the maximum boundaries. And the concept of potential barrier is very important for you to know whether that units get truth, what is going on. When the diode is working or it's not working. So if that's the case, in any configurations of the diode, so we are going to have this one. The maximum voltage is equal to what? Stop writing. So this is figure what? Anastasia, this is figure number 2, The schematic circuit diagram of 40 bridge rectifier. So maximum voltage will be equal to what? Voltage across diode 1 or diode 2 plus voltage across diode 3 or diode 4. But we expect this bridge rectifier, after it works, or after we feed the input, we expect to get the output from it. Right? Right? And the output we use to draw it from here, from these two terminals. Stop writing, look on the blackboard. We've been discussing about the input of the rectifier, which is we say we are going to take the parameter of maximum voltage or peak voltage. Okay? Okay? Then we discuss how does the rectifier work. So the third part, once the rectifier performs the function, it has to give the output. So the principle of opening this block, you have to think about what the input, what is within or what is the controlling unit within that block, and what is output. Are we together? Are we together? So for that case, the output from these schematic circuit diagrams, we are going to draw it here. So this one we say V out of the rectifier. So if that's the case, we have voltage supply, which is VP. Here we are going to have a voltage drop. And here we are going to have a voltage drop. Then here we are going to have a remaining voltage. Are we together? Are we together? Huh? Johanna is kind of slumbering. But he told us yesterday to pray for him. Did we pray for Johanna? Samandito? Because he's slumbering now. He managed to come to the class. He didn't tell us whether he's doing well or not. But now, so maximum voltage is equal to VD1 slash VD2 plus what? VD what? D3 slash D4 plus V out. So if that's the case here, we are still missing V what? V out. So you have a potential drop and potential drop. We have a remaining voltage after providing the voltage across the 1 or 2, the 3 or 4. Okay? Okay? So we go back to the topic of exponent and radicals that we learned in basic mathematics, Form 2, the first chapter, among 11 topics of Form 2. We have V out is equal to what? V peak minus what? VD1 slash D2. Minus what? VD3 slash D4. Are we together? Huh? I just made this a subject. Huh? Even make the subject is a problem for you nowadays. You're a veteran. Are we together? So for us, we just chose a step-down transformer of 40 that provides output voltage of 40, 12, but root mean square voltage, right? Then we computed its maximum voltage. What's the maximum voltage, Pili? 16.97 volt. So these are the silicon. Mostly we use silicon, but you may be given germanium. So you should not cram. Right? So the voltage drop here will be what? 0.7 volt. Not 1.4, because the two diodes which you have indicated here, they are not conducted at the same time. Okay? Okay? Then minus what? 0.7 voltage. Voltage across the potential barrier of diode 3 when it's conducting, or potential barrier of diode 4 when it's conducting. Are we together? Are we together? Class, are we together? So we are going to have 16.97 V, then minus 1.4 voltage. What do you get? Pardon? Simple. You just take 7 minus 0, 7. You are just sitting in a calculator to do this simple subtraction. Then we have what? 9 minus 4, 5. Then we put a print. This is how we learn mathematics those years, when you didn't know that there is something called the calculator. 6 minus 1, 5. 1 minus 0, 1. You are done. But now, because you have a calculator, you say, I will be spending much time. I'll be spending what? Much time. Okay, so that is V out of 40, but this is V out of rectifier. But this is no longer root mean square. Rectifier unit is equal to 15.5 volt, 57 volt. So from there we can have our simple table. Our simple table, which you can call it table number 2. The table of result of what? Of congratulations, rectifier unit. So you select our table to have the harmony, to have 4 columns. So here we have what? Electric parameter, or sometimes we call it testing point, electric parameters. And here we have what? Calculated values. And then here we have what? Simulated, yeah? This way. Simulation. Yeah? Simulated values. And here we have what? Measured values. So in case of the rectifier, we just have what? We just have input, maximum voltage. And also we have what? Output, still maximum, or we assume that something is equal to ODC voltage. So here we had what? 16.20. Dominic, 16.20. 97, Dominic is silent. Then output maximum voltage here we go to 15.57 volt. Did you leave any other parameter? No. Then now ask your neighbor, what the nature of the graph of the input signal to the rectifier unit and output signal from the rectifier. Ask your neighbor. Ask your neighbor, please draw the graph. The graph of input. So everybody has to draw for his or her neighbor. So draw and then show your neighbor. Quickly. Just draw what you are thinking about input, graph, and output graph. Are you happy? Sure. In what extent? But you are not okay. Somehow. So you are getting well. Don't discuss. Draw what you are thinking about input, the graph of the input voltage, and then show your neighbor what you are thinking. And the graph of the output of the rectifier. Just draw. Don't bother yourself whether it's correct or not correct. But try to draw what you are thinking. There's no need for you to draw even by using a pencil. If you spend much time on drawing by using a pencil, just draw because it's a rough drawing. Some students, they don't have neighbors. They are just copying. They are still copying. Draw the graph for your neighbor. That is your neighbor. So your neighbor is watching. Neighbor, please don't copy from your neighbor. Because our neighbors are just have magnifying glass. Have you drawn? Did you show your neighbor? Who is your neighbor? Who is your neighbor? Did you show you? And you? And him? So, can I see? So you expect to get this one practically. And there's no parameters. Eh? So now you're finished to draw and show your neighbor. Now we are discussing some other stories, isn't it? You are making story. You are socializing. But try to check your neighbor's graph. Do they look like mine? Or they are very special? Eh? The graphs of your neighbor are very special or they look like mine? Okay, good try. Let us do the correction. So he said that graphs of what? Graphs of input and the output voltage of rectifier, graphs of input and output voltage of rectifier unit. So you can draw the individual graphs, or you can draw the combined or one graph by presenting the input and output. So I know that you've been expert on drawing one graph. Let me teach you how you can draw, on drawing two different graphs. Let me teach you how you can draw the two graphs, the graph of input voltage and output voltage on the same figure. Okay, so stop writing and stop drawing. So you can see what the value that I'm going to add from what I told you, I introduced it to you last time. So this is equal to maximum voltage, positive maximum voltage, and this is negative maximum voltage. Wewe! Nimesema acha kuchora, stop writing, stop drawing, look on the blackboard. I gave you more than 5 minutes. And they've been making some other stories which are not related with engineering. So we are going to draw the so this is the graph of input voltage. Okay? Okay? But remember that the maximum voltage, the max of the maximum voltage, V peak, is 16.8. You have to use the scale if you're drawing on the graph paper, 16.97 voltage. And here we have negative what? Negative V peak, so the same value. Okay? Then, you're clean. Then, we are going to draw out the graph of the output. So this is input voltage. Input voltage to rectifier unit. Then when you think about the pulsating voltage or the theoretical graphs, because we'll analyze them and see them if they are correct. The pulsating now will be in this form. I know that what you drew to your neighbor, you didn't care about what you've been discussing, you didn't link your graph with the calculation that you've made. We say that the maximum voltage of this pulsating voltage we have computed there. I know that you didn't present to your neighbor the out, so here we have the out. The out of the which is 15.20, 57, or 47. 57 volt. Similarly, so for this side we don't have it. So for you, you could have just drawn the pulsating. You didn't care. You don't care about the relationship of the magnitude. Okay? Okay? So now you can mark your neighbor's graph. I know that you can create even the politics. That, my neighbor was correct, but just the value. Just what? Output voltage of rectifier unit. So this is the figure. So if you do remember, last Saturday I drew them separate. I drew them what? So for those who say that this is repetition, it's the actual repetition of what you have learned. I wish you a good luck. And again, it does not mean that I've discussed everything about rectifier. There's a hidden knowledge again, still there. The graph of what? Of input, I told you that, and the output voltage of rectifier unit. So when you be simulating this part, or you go for simulation, you have to try to prove what you've been learning theoretically. And that's our tomorrow's responsibility. Right? Right? When you go for the hardware implementation, you are building the rectifier. You have to think, how can you verify the theory concepts that you've been learning? You should not just say, the rectifier, the bleed rectifier, convert AC to DC. Have you ever seen? How can you give the evidence that the output signal now is DC, not AC? One of the techniques is by using the graph. Class, is it clear? Okay. If you have any question about rectifier unit, please ask. Dixon has a question. Speak English, please.
Operation of rectifier, we will not talk about the filter, which is necessary for smooth the output current. My question is that the filter is not necessary.
So Dixon, he said, his question is, when you talk about rectifier unit, are we not supposed to talk about filter unit? Because this filter is the one that's smoothing. What the answer of that question? Filter unit is the filter unit, rectifier unit is the rectifier unit. So we've just discussed about rectifier unit. We are heading to the filter unit. Another question? Did you understand? Yes, that is all about rectifier. It does not relate with anything about a filter. Filter is filter, rectifier is rectifier. Another question? Simon? Daniel? Fulgence? Gaudens? Sorry. Latifa? Nora? No question. Mvunye, you have a question? Your name is? Edgar? Edier? Edson? Edson or Dixon? Edson,
My question is that when you draw the output voltage graph, so that the graph is linear, so that compatible DC completely. But instead the graph is not complete complete. The graph on it will show the component.
Where? The output graph there is it's linear. The output graph there. Class, is the output graph, is this graph linear or not? Is this a linear graph? So our friend there made a confusion. These are just the values, the maximum values. This is not a graph. I can even delete them. They are not a part of the graph. They're just showing that this is the maximum value. So these points, they have the same value. I can even just delete this one. They are not a part of the graph. As long that you use the graph paper. So it means these dotted lines represent the lines you found on the graph paper. Okay? Okay, Edison? Yeah. The last question from Ruben. Yes. Speak loudly, because that's why I bring the microphone nearby you. So his question says that why these are so the Ruben's questions is actual intending to explain what's going on within the OT, within the diode. He said that why this graph, what actual that Ruben is expecting, expect that this graph to be in just this is positive half cycle and this one to be in the negative, right? So there's a lot of information that make this graph to shift it to here, which I cannot speak about them in this workshop. Okay? So simply just know that when you pass alternating voltage into the diode, finally we find that this one is shifting up. Shifting up. And the simple reasons mean that. The simple is, let me just give you a simple description, but it's not all about what. Remember that this one, it means when we conduct it, so the principle is this one. When the positive half cycle are approaching the two diodes, right? Then, at the same time, also we have a negative half cycle. So this one will conduct. Before going to the next half cycle, then this one reverse, become the positive, while this one become the negative. The principle is this one. Okay, let's just give you this principle. Listen, we said when this is positive half cycle and negative half cycle, the diodes which will be connected to the positive half cycle will conduct. Right? So here we used to write that here we have diode 1, let's say diode 2, and the diode 4. Right? So then within 0.01 second, the process change. This negative half cycle become positive half cycle, while this one become negative half cycle. At that times, diode 1 and diode 3 conduct. Okay? The process again, so this one or this one just change, become positive. So it's become positive, diode 2 and diode 4 conduct. So that's the process. Okay? So we are done with rectifier unit. I've received these 3 questions. I know that you might having more questions, more than even 3 questions. But to keep focus on where we are heading to, let us say that we have covered some information about rectifier unit. So now let us go to the next block, with the third block, which is filter unit. Say filter unit. Say filter unit. Write it down. If you have a question, write it down. Time is not our side. So simply we say that filter unit is a part of linear power supply, which filter the power signal. In electronics, we have filters which are filtering the power signal and filters which are filtering the data or the information signal. We have communication filters or electronics filters, and also we have power filters. So power filters actually are focusing on filtering the power. And these power filters, we use them when we are converting one form of power into another form of power. So you say that the filter unit, filter, so the filter unit filter or filters some AC signal. AC signal which the rectifier unit, the rectifier unit fail to convert it into DC signal. So why do we need filter? From this output graph of the filter unit, we find that we have kinds of the DC signal. But that DC signal is not pure DC signal. So if it's not pure DC signal, what does it mean? It means it's a DC signal in a large extent, but contains some AC signals. So from there, it means that we don't have a constant DC signal that we can supply to our electronics component, because our electronics components need the constant power supply. So in case we take the outputs of the rectifier unit and feed it to any electronics components, then that electronics components is going to malfunction. Why? Because it has been fed the power which it cannot withstand. So I think that last time I just made a mistake. I said the output of rectifier units is called the, okay, sir, the pulsating signal. You see, you made mistakes. Rectifier unit, rectifier unit. So the output signal of the rectifier unit contains some ripples. So the output signal of rectifier unit contains some ripples. Then a ripple or ripples, it's a vocabulary for many of the students. So let us discuss a little bit about ripples, because we are heading to there. Say ripple. Say ripples. Say ripples. Ask your neighbor, will you call your firstborn ripples? Or will you call your firstborn linear power supply? What is ripple? So he said that a ripple okay, so we have ripples, but the main focus here is ripple factor. I'm not going to talk about ripples in detail, but ripples, it means that they are AC in nature, and also they have its particular, or they happens when we are converting power from one form to another power, whether it's from AC to DC or DC to AC. So what is ripple factor? So the ripples, we may measure them by using the ripple factor. So ripple factor is an important parameter to measure the amounts of the ripples that have been processed or within the circuit. So class A, ripple factor. Again? A? Ripple factor is a ratio of the root mean square value of alternating current component in the rectifier output to the average value of rectified output. Rectified output. So a ripple factor is a ratio. Say ratio. Say ratio. Ratio is something over. Something over. Is a ratio of 40. Root. Do you know root? A. Root means square what? A. Of what? A. Alternating what? Where? In the rectifier what? Not rectifier input. To the what? Average of what? A. So can you write the equation of according to that definition? So, once you have a definition, just like what is current? Current is the average of voltage over is a ratio of voltage to the resistance. Okay, so there's a lot of stories and there's a lot of things to cover about ripple in electronics. Very important parameter, especially if you're discussing about linear power supply and switched mode power supply. So the context of ripple actually is broad. So I don't have enough time to talk about it. So just I've given you some few information. We are going to deal with ripples or to just eliminate those ripples. And then to get the output voltage or just the DC and regulated DC voltage. Possibly also kinds of varings because it originates from the alternating voltage or alternating current. So then the next part, the concept of ripple factor has more than 3 equations, but the one that we have to recall, so I'm going to write the one that we are going to use in our computation. But before we just I write that one, so we say that in design of in the design of linear power capacitor, power supply, we use what? We use the capacitor to filter or remove ripples from the output signal of the rectifier unit. So we are using electrolytic capacitor. We are using electrolytic capacitor. Say electrolytic capacitor. Again. How many types of capacitor do you have? 2, eh? Which? Polarized D&D? So that is the 2 types of capacitors according to the polarization. But according to the dielectric material, How many types of capacitor do we have? Eh? You forgot. According to the dielectric materials, how many types of capacitors do we have? Many. How many? They are countable. Are they many like the sand? Or they are many like stars?
They are just like 5.
5. The first one? Maker capacitor. The second one? Paper capacitor. The third one? Electrolytic capacitor. The fourth one? Variable.
They have
Evaporated.
evaporated.
Okay, so this capacitor actually we use to filter or to remove what? Ripples. From what? This is from. Not the front. From what? From the output signal of the rectifier unit. So from there, it means that I assume that you know about ripples. If you don't know, I've introduced to you. You may go and learn in detail. Recall the ripple, the ripple factor. Joshua was doing something. Ripple factor equation. Ripple factor equation. The ripple factor equation, we have ripple factor is equal to 1 over 2 square root of 3 times resistance of the secondary coil of transformer or step-down transformer times capacitance that we'll be using for the filtering times frequency. Isn't it? So this is the ripple factor equation. Ripple factor what? Peter, ripple factor what? Peter, ripple factor what? Question. Ask your neighbor left hand side, right hand side. Where were you, or where will you be in your own life in 2034? It means 10 years ahead, 10 years later. Where will you be? Ask your neighbor. Where will you be? What kind of life will you have? Will you be electronics engineer or electronics politician? And tell your neighbor that 10 years ahead, so this is the resistance of what? Of the secondary coil of step-down transformer. You are still asking your neighbor? Are you still asking your neighbor? Eh? And what did your neighbor say? He or she'll be what? A member of parliament or a prime minister? A prime minister of what? Electronics? Or you will establish what? A software company or a hardware company? So this one represents capacitance of the capacitor. There's a difference between capacitor and capacitance. Just like there's a difference between resistor and resistance. Hey! So then where F will stand for frequency of output signal from the transformer. So if this is the case, we can call this one equation 1. So we know what the frequency of the output is signal from the step down from the transformer. 50 Hertz. Then what the resistance of the secondary coil of the transformer? You don't know. What the capacitance that we are going to use, we don't know. That's what we are going to calculate. What the ripple factor that, which are ripple factors of most of the linear power supply, it's 7%. So you say the ripple factor of linear power supply is 7%. So this means that Y is equal to 7%, and Y is equal to 7 over 100, it's 0.07. 0.07. But again, we need to calculate resistance of the secondary coil. So the resistance of the secondary coil, we can compute it from the maximum output voltage over maximum output current. Okay? So you might think that, or you might see that, here we see the importance of the parameters or specification of the transformer. Christina, what's going on upon your friend? He's not in this class. So if this is the case, this will be question 2. So the theme to recall these ripple factor equations in order to calculate the capacitance which will be suitable or will be fit to remove all the ripples within our linear power supply. That's the aim of recalling ripple factor equation. That is Omolo, Ohoro, the other name? Orao. Omolo, Ohoro, again. So let us make the capacitance the subject here, right? So capacitance is equal to what? Is equal to 1 over what? 2 under of 3. Then times what? So for the resistance of the secondary coils, we'll use maximum voltage over output voltage over output current. Then multiply by what? Ripple factor. And then multiply by what? Frequency. So you may keep on simplifying this equation. You have the output current. We have 2. These are the simple stuff for the A-level students or diploma students. This is simple stuff. Just to do this, it's just make it a factor and simplify. So Omolo was omololing. And Ohoro was what? Where? Massa. C is equal to what? What the output current? Let me write here, because some students there are slumbering, so they cannot see what I've written there. Maximum voltage, frequency, ripple factor. And what the output currents of the transformer, of the step-down transformer that we chose? 5 ampere, 100 ampere, 500 ampere. Refer the table that we made in workshop 3. Refer, because now you forgot. Why are you not writing? Huh? 1 ampere. So now you say it's 1 ampere. Others they are saying 500 milliampere. Those who have written in previous, they are not updated. They are still there. So what the maximum voltage from the step-down transformer? 16.97. Not the output voltage from the rectifier. Be careful. Then what the frequency? 50 Hz. Then what the ripple factor? 0.07. Compute that capacitance. You're using calculator. Can I have a calculator? Because you might spend a week to calculate that parameter. No, I don't like, I think I prefer that one. We have 2 times square root of 3 times 16.97 times 50 times 0.07. What do you get? 4.8. 4.8 what? 6. Exponent what? -3. What the unit? Why Farad? Why Farad? Why Farad? The essence of capacitor. Yes, we know Farad is the essence of capacitor. How did he get Farad? Farad is a milliampere. Simply, we say that, we taught you that if you want to compute capacitance, is equal to quantity of charge over voltage. The quantity of charge also is equal to current times time. And the voltage is voltage. There's Anastasia. The SI unit of quantity of charge is Coulomb. And the SI unit of voltage is volt. So we get Farad after taking the Coulomb divided by voltage. But if we refer this equation, we don't have Coulomb. And don't have, possibly we have just the voltage. So how did he deduce? Or how do we get that parameter of what? Parameter of capacitance over, or actually at Coulomb over voltage, which is equal to Farad. Simple. Here we have been calculating capacitance. The SI unit of output current, Samuel is busy, is ampere. But we know that this output current is equal to a quantity of charge over time. Right? How do you get it? I. If make I is quantity of charge over time. So the ampere, in other words, is equal to Coulomb over second. Okay? Then here we have voltage. Our maximum voltage. The unit is voltage. Then here we have frequency, which is what? 1 over second. Right? Frequency is equal to 1 over period. Then you have ripple factor, which is unitless. So if we simplify this one, it means that how do we get this Farad? So for this case, here we have Coulomb over second, and here we have voltage over second. So second and second. Jacqueline is not busy. Jacqueline is busy with something else. Jacqueline is writing. Jacqueline is drawing about the physical appearance of bridge rectifier. I know what you are doing actually, because I skipped that part. But if you check your neighbors who attended, yes, he drew the physical appearance, the bridge rectifier IC. So those who were not there, I know. They took the exercise book of their neighbors and draw. But they don't know what are they drawing. Because in Bongo, understanding comes later after copying. And understanding is not important. The important is cramming. Okay? So here we have Coulomb of voltage. Yes, you have to think how the units cancel in a mathematical equation. Don't say that because there's a unity of capacitance is Farad. Sometimes you can find some of the units that have been used in the equation. They don't give you the specific or that is specified as a unit. So from there you have to reason. And especially you have to question about the equation that you have. Because the challenge of the many students, they know, okay, what is the unit of capacitance? is farad. What is the essence of current? It's ampere. What is the essence of charge? Is coulomb. But they don't think about the relationship between one unit of the physical quantity with another unit of the physical quantity. So that if that's the case, you might use even a wrong equation to do the computation. Okay? Okay? So this is just to clarify, because you know this is tough. So the unit here is farad. So most of the capacitors that they have in electronics are not in unit. There's no actual. Most of the capacitors are not in. Yes, we have, because we have ceramic capacitor, we have electronic capacitor, and also we have what is super capacitor. Super capacitors, they can have some farads, but actual we don't use them in filtering the pulsating signal from the filter. So simply say that I have to remind you that 1 farad is equal to 1 exponent 60 microfarad. And also, this is the case. 1 farad is equal to 1 exponent 6 microfarad. But also remember that 1 microfarad is equal to 1 exponent negative 6 farad. So if that's the case, so it means that in order to convey it or to express this capacitance into farad, it's simple. We just use this conversion. 1 farad is equal to 1 exponent 60 microfarad. How about 4.86 exponent to negative 3 farad? This is equal to what? So we cross multiplication. So it means we find that the capacitance is equal to 4.86 multiplied by negative 3 multiplied by 10 exponent 6 microfarad. So the capacitance is equal to what? 4,800 and 600 microwatt. Right? 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 These are the common questions that will be asked in your final year project presentation during your studies of Bachelor in Electronics and Telecommunication Engineering. You'll be asked, how did you come? Because there, many people, they used to quote from the previous book that always the filtering capacity is 1,000 microfarad. So they lie. They just calculate like this, say, I took a transfer of 1 ampere. They just do this one, and then finally they write 1,000 microfarad. So if that's the case, that's the calculated value of 40. Capacitance of 40. Capacitance of 40 class. Capacitance of 40. Capacitor. But practically, we don't have a capacitor that have a capacitance of 4,860 microfarad. Because capacitors, resistors, inductors are always manufactured in a standard value. So we have standard values of capacitors, which I cannot talk them because that is, it's a class of more than 2 hours. So the key point that I want just to let you know that capacitors are manufactured in standard values. So you cannot find a capacitor of capacitance of this magnitude. So if you go to the shop, don't think that everything you calculate is corresponding to what you have in practical. Okay? 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 Yes, because I know sometimes you can be given to design something, you just made a calculation, and then you get that one, you say, let me go to the shop and buy. I need a capacitor of 4,860 microfarad. It's not there. Even you order in China, it's not there. Okay? So when you are dealing with passive electronics components, especially resistor, capacitor, and inductor, you have to know the standard values, because those standard values are the ones that you can go and find in the shop, or you can go and find somewhere else in an electronic shop. So if we say that, 480 microfarad is not the standard what? The standard capacitance of 40 of the capacitor. So the standard capacitors which have capacitance nearby this are 2. We have a standard capacitor, standard capacitors of what? We have a standard capacitor. We have the some standard capacitor of the nearby values. So you have standard capacitor of 2,000, 2,000. I think that 4,000. The previous one was what? 2,000 what? So the range I gave 2,400. So this is the homework. So listen, we can have, so this actually this will be in between of the two capacitors. We can have a standard capacitor 1 here, and this is the calculated value of 4,860 microfarad, and you can have a capacitor 2. So this one, it's a standard capacitor with capacitance less than the calculated, and this one, the standard capacitor with a capacitance greater than the calculated. Can I repeat? Can I repeat? Here we have three standard capacitors. We have C1, we have C3, let's say, we have C2. So C3 always will be lying between two standard capacitors. That is Peter. So C1, the capacitance of capacitor 1 is less than the capacitance of the capacitor 3. Right? The capacitance of capacitor 2 is greater than the capacitance of capacitance 3. Right? Right? So for instance, I want just to leave this task for you because previously I gave the standard capacitance of the capacitor. I want to leave this task to you to go and look. For instance, this one you might find that it's 400, let's say it's 400, 400 and 600, 4,600 microfarad. While this one, maybe I just took assumption, 5,000 microfarad. So 4,000, the capacitance of capacitor, 4,860 microfarad lies in between. Right? Right? But always, whenever we make a choice, we choose the standard value which has a greater value rather than the calculated. Are we together? So if you're being asked to choose, it means capacitance 2 is suitable or is actually capacitance 2 is chosen over capacitance 1. Or capacitor 2 is chosen over capacitor 1. This is standard capacitor, this is the standard capacitor, but this is the calculated. So this is the capacitor with calculated the value of capacitance. Right? Right? These standards are declared by the manufacturers of the capacitors. There are companies and industries responsible to manufacture capacitors. So whether it is in United States or in China, the standard is the same worldwide. Okay, class. So this is the homework. Homework. So the homework is this one. Question 1. Choose the standard capacitor for filtering. The second question, choose the standard capacitor for what? For filtering. The second question, choose the standard capacitor for filtering. Second question, draw the table of result for filtering unit or filter unit. The third question, draw the graph. The graphs of, so draw the graphs of 40. Draw the graphs of, the graphs of 40. The graphs of input and the output voltage. Or filter unit. So when you manage to do those 3 questions, actually it will test your understanding about how you have to speak engineering by using the 3 or by using the 5 parameters or the 5 components. Okay? So go and think. Don't just go and copy from the internet. Try to think what we've fed here and what will be the output. Okay? So if that's the case, I would like to say that this is the end of workshop 4. And in case you have any question, you may keep on asking because learning does not end. Otherwise, let me invite you in workshop 5, where that will do just the corrections of this homework, and also we'll be discussing about the voltage regulator unit. And from there now, we'll draw the overall schematic circuit diagram. So overall schematic circuit diagram, because I want to teach you the linear power supply concept in broad context. Because sometimes you might know how to design the linear power supply which provides the positive voltage or the single output. But in some cases, you might need to design a linear power supply that is capable to provide more than one output voltage. Or in some cases, for example, if you want to deal or you want to build or just to design a linear power supply that you are going to use in operation amplifiers. So any operation amplifier, especially either it is inverting or non-inverting, it needs the positive DC power supply and negative DC power supply. So the concepts of linear power supply is not simple and narrow the way that you might be thinking. It's broad because in electronics, we might need the positive voltage or we might need the negative voltage. Another case that we can have a system or maybe a particular system in electronics, which I say stop writing, listen. You are writing and closing your exercise book. Ready to? Let me repeat. I said, I would like to ask you to join me in the next workshop 5 and workshop 6. We'll be still discuss about linear power supply, but in broad context. So what are we heading to? It's not just that we are going to build a power supply, but remember, in electronics, we can have a system of an amplifier where we are going to use the operation amplifier. For instance, that maybe summing amplifier. You want to design a summing amplifier, which will be just having 2 or 3 signals, just supplying the input in order to be summed to give the single output, right? For that case, your system, you will need a positive linear, positive DC linear power supply and negative voltage or negative DC linear power supply. In some cases, especially that if you're integrating say the filter that you want to implement or to build an electronic transmitter and electronics receiver, for that case, there are some components which actually draw a large amount of power. So you might have maybe a system which needs Boniface. You can have, for instance, a same system. Some of the parts of that system might need a positive 5 voltage. Some of the parts of that system might need the operating voltage of 9 voltage. Some of those operating, some of the parts of that system, might need 12 voltage. Some of the parts in that on the same system might need 15 voltage. Some of the parts in those systems might need negative 12 voltage. So you cannot get all of this voltage by designing a single linear power supply. And we don't need, we should have a single, but we should have actual different ways of actual that having the different output. So when I told you the concepts of the transformer, I'm going to teach also the concepts of the regulators. And regulators actually also is going to do some decision in order to provide you. And something you can design to just a linear power supply which providing 2 or 3 outputs of the same voltage. But those those voltage will be used in particular in subsystem. Another voltage will be used in subsystem. Another voltage will be used in subsystem. Why should we do that? Because sometimes you might find that the voltage regulators, especially we have in electronics, most of them, the maximum current is 1.5 ampere. Sometimes you can design a system which needs 2 ampere. For that case, you cannot use a single voltage regulator because your system, some of the parts are not going to be powered. And if are not going to be powered, they won't work. Are we together? So that's always I tell you that there's another incoming OT story. There's another incoming OT story. Don't limit yourself that, I know how to design a linear power supply that provides 5 volts. No, that will be using in case that you need only 5 volts. And sometimes if you have a large system, the single linear power supply of 5 volts cannot help you. So this is the end. Thank you very much. May God bless you. See you in the next workshop.